Hello everyone, welcome to the IGCSE Physics predictions for paper 2 for your exam tomorrow as in June 2026. So these are the topics that are unique to paper 2. Please remember these are not the only topics in paper 2, right? Anything that's in paper 1 can also appear in paper 2, right? But since these are the topics unique to paper 2 and these are most likely to appear in your exam, we'll be focusing more on these ones. And in the description, I have given the FAQ sheet, as in the frequently asked questions. As you all know by now, that IGCSE is very repetitive. You get the same questions in the twisted form every single year. And with the FAQ sheet, you will get a free definition sheet as well as an experiment sheet. And I can promise you, you'll get a lot of questions common from the FAQ sheet and definition sheet as well as experiment sheet in your exam. So let's get started. Okay, so here I'll only be touching the topics and giving you my idea of what are the topics that are most likely to appear. I won't be getting into like extreme details about the concept of any topic. And if you want to brush up your concepts, there is another full syllabus revision video, or as I call it, last minute revision video for paper 2, and the link is given in the description. Not download link, this is just the watching link. All right, now first, momentum is a unique topic of paper 2, right? So let's look at the three scenarios. In first scenario, a moving object comes and collides with a stationary object, and they, after the collision, they move in the same direction, but not touching each other or not together. So in questions like this, I always ask my students to write down a base equation that helps them a lot. So the base equation for this scenario could be like this. Check this out. So let's say this is m1u. This is the total momentum before collision because this one is at rest. And after collision, both of them are moving. So m1v1 plus m2v2. So my suggestion would be write down the base equations for any scenario and then start plugging in the values. So this reduces the chances of making mistakes. This one, both of them are moving, but they're moving in opposite directions. So m1v1, since it's moving in the opposite direction, it should be minus m2v2 equals to, and after the collision, they're moving in opposite directions. And finally, for the third one, they're moving in opposite directions, and after the collision, they stick together and move off together. So for this one, total momentum before collision is m1. Instead of v, it's better if you write u. u1, u represents initial, plus m2, u2. And bear in mind, since it's moving in the opposite direction, there should be a minus sign here. Minus into u2 equals to, and since they're sticking together, when two bodies stick together, always add up their masses, m1 plus m2 times v. And this is the common velocity with which they move off together. Next. So we have seen law of conservation of momentum in collisions over here, but this also applies to explosions as well. And when it comes to explosions in physics, it doesn't mean that there has to be a chemical reaction. In physics, explosion simply means two bodies starting together and then they're moving apart, right? So before the firing, they were together, and after the firing, they move off in opposite directions. So you can apply law of conservation of momentum in here, like total momentum before firing is 0. So total momentum after firing must also be 0. And to conserve momentum, the ball and the cannon move off in opposite directions with equal and opposite momenta. The same concept can be answered using Newton's third law as well. And again, Newton's third law is also a topic unit two, paper two, I mean, right? So uh, the cannon exerts a force on the ball forward. According to Newton's third law, the ball exerts an equal and opposite force on the cannon backward. There is a resultant force on the cannon backward, causing it to accelerate backward. Then uh, let's analyze Newton's third law. So for two forces to be Newton's third law pair forces, it must fulfill 5 conditions. And these are the conditions. The forces must be equal in magnitude. The forces must have the same line of action. The forces must be of the same type. The forces must act in opposite directions. And the forces must act on two different bodies. But let's take a look at the scenario on the left. A block is resting on a surface. So the two forces acting on it are weight and reaction. So weight and reaction, even though the forces are equal in magnitude, they have the same line of action, and the two forces are acting in the opposite direction. But you still cannot call it Newton's third law pair forces because 5 out of 5 conditions must be met, not 3 out of 5. The reason they are not Newton's third law pair forces is because these two are not of the same type. Plus, for Newton's third law pair forces, the forces must act on two different bodies, whereas these two forces are acting on the same body. So since these two conditions are not met, weight and reaction cannot be construed Newton's third law pair forces. Next, let's say this is a wheelbarrow, okay? And this is a common concept in paper 2. They can ask you why the two forces are not equal, okay? So for this type of question, you are considering moment about the center of gravity as in G. We are considering the moment about this point. Okay, so about this point, R is creating a clockwise moment and P is creating an anti-clockwise moment, right? So if the body is at rest as in equilibrium, the moments are equal, even though the two moments are equal. Moment equals force times perpendicular distance. But check this out. The two distances are not the same. Since distance from the center of gravity to R is smaller, the force must be greater because both of them are producing the same moment. And they can even ask you to calculate one of the quantities, okay? And when it comes to moments, you can take moments about any point, okay? So previously, in this scenario, you were taking moments about this point, but for this calculation question, you'll be taking moments about this point. So what does the question say? Determine the horizontal distance between the center of gravity of the wheelbarrow and the center of the wheel. Right. So center of the wheel and center of gravity is over here, what we previously saw. Now, since the wheelbarrow is at rest, right? When something is at rest, all the forces are also balanced, right? So these two are upward forces, and this must be the downward force, which is basically the weight. And these two forces balance this weight. So 320 plus 80 gives you 400. Since it is at rest, as in equilibrium, all the upward forces must be equal to all the downward forces. And there is only one downward force, that is the weight, 400 Newton, right? So when you are taking moment about this point, sorry, and this. Always remember when you apply principle of moments, by the way, they can ask you, what do you mean by principle of moment? And the answer is given, and all the definitions are given in the definition sheet. So make sure you have reviewed all the definitions. Now, this force is not producing any moment about this point. Why? Because there is no perpendicular distance from this position. So there is no perpendicular distance. So when you are applying principle of moments is always total clockwise moment equals to total anti-clockwise moment. And while applying, always remember, you are always considering the distance from the pivot to the force, but the perpendicular distance. So this 400. So the question asks me to find out this distance. So 400 times x gives you the total clockwise moment, and 80 times, this is the perpendicular distance from 80. 1.5 gives you the anti-clockwise moment. So this is the clockwise moment, this is the anti-clockwise moment. And all you have to do is just make x the subject of the equation. Next, you have static electricity, which is also a core concept of paper 2. So these are some common questions that can appear. How does the rod become? Okay, check this out. Positively charged. If the question had just asked you how does the rod become just charged, then all you had to say was there is a transfer of electrons due to friction when the rod is rubbed with the cloth, right? So there is a transfer of electrons due to friction, and that's it. But if they specify that how does it acquire the positive charge, then you need to mention, is it gaining electrons or losing electrons? Always remember, if a body loses electrons, then it becomes positive, and if the body gains electrons, it becomes negative. So what happens is, when the rod is rubbed with the cloth, the rod loses electrons and becomes positive, and these electrons are gained by the cloth, and the cloth becomes negative. So the next question says, how do the magnitude of the charges on the two compare? So guess what? So the amount of electrons that this one loses is gained by the cloth, right? So they have equal and opposite charges. So the same amount of charge, the only difference is one becomes positive, the other one becomes negative. And there is also a common question, how can you demonstrate that there are two types of charges? Okay, so you suspend some rods, charged rods, and you bring another charged rod near them, and some rods will attract, others will repel. So attraction and repulsion show that there are two types of charges. Also, when it comes to static electricity, you need to be aware of the risks involved in static electricity. Okay, so we always do grounding because while refueling aircrafts or tankers, um, rubbing when the oil rubs against the hose, it can acquire a charge, and spark can lead to an explosion. So the safest way is to ground the airplane or ground the tanker. So by grounding, what you're doing is making it neutral. Okay, so there is current flowing in the earth wire, and how long does the current flow? Until the object becomes neutral. When the object becomes neutral, there is no flow of charges or no flow of current. Next. So when it comes to waves, you have a very common concept of determining the time period or frequency from oscilloscope while studying sound waves. And what do you connect to detect the sound waves? You connect a microphone, right, to detect the sound waves. So anyway, so this is the trace on the oscilloscope, and the question says, determine if the sound wave displayed on the oscilloscope could be heard by humans. All right. So always remember, in x direction, every square gives 20 times 10 to the power minus 6, right? So this is what you call the time base. One square in the x direction is called the time base, right? So the first thing we have to do is count the number of squares for one complete cycle. I can start counting it from here. So 1, 2, 3, and 4. So this shape represents one cycle. I could have also started from here. And if I start from here, I end over here. This is a cosine curve. And again, 1, 2, 3, 4. So in either case, 4 squares represent one complete cycle. So the time period would be number of squares multiplied by time base, which is 20 times 10 to the power minus 6. So 4 times 20 times 10 to the power minus 6 gives you 8 times 10 to the power minus 5 seconds. But the question asked if the sound can be heard by humans. This is where you have to bring in the frequency, because you all know that the human audible range is given in terms of frequency. So F, as we all know, is 1 by time period. So 1 by answer gives you 12,500 hertz. And the human audible range is 20 hertz to 20,000 hertz. And since this value is within that range, so of course this sound can be heard by humans. Next. When it comes to energy resources, you need to know all of the advantages and disadvantages of each energy resource. So you have fossil fuel, nuclear, wind, solar, hydro, tidal, geothermal. So these are the advantages and these are the disadvantages. And they can ask you, which one would you prefer over the other? Okay, so this is where you have to bring in the advantages and disadvantages. And also you need to know the definitions of renewable and non-renewable energy sources. Now, energy stores and transfers is also a common concept appearing in paper 2, even though this is more commonly in a paper 1 context, but this can appear in paper 2 as well. Now, the question says that there is a solar panel on top of this microbus. So describe how energy is transferred from the sun's energy store to the battery's energy store. So you have to separate and segregate stores and transfers, right? So when the sun radiates, right, the nuclear energy store decreases in the sun because the nuclear store is being converted to some other store. And energy is transferred by radiation. Guess what? Radiation is a form of energy transfer. So for transfer, it is radiation. Energy is then transferred electrically. From the solar panel, there is a battery inside. So from the solar panel, there are, of course, wires connecting the battery and current flows. And if current flows, the energy is transferred electrically. And this current charges up this battery. So battery stores charge by increasing the chemical energy stored of the battery. Next. For unit 5, you have a very common concept of arrangement and movement of particles in solids, liquids, and gases. So always remember, in solids, they're arranged in a regular pattern and the particles are close together. And for the movement in solids, they vibrate about fixed positions. And when it comes to liquids, they are irregularly arranged and they're still close together, but it's just not regular like solids. And they slide past each other in random direction. And they're also arranged randomly. And when it comes to gases, they are arranged randomly and they're also far apart. And they move randomly in high speeds, move quickly in high speeds. And these are the diagrams for solids, liquids, and gases. For gases, you can make it even farther apart. And in the very recent mark schemes, I'm noticing that they ask you to, and they prefer that you give some particles touching each other. Some they have gaps between them, and most of them are touching each other. So this has become a norm in the recent papers. Okay. And then you have graphs of cooling and graphs of heating. So let's start with the cooling curve. Let's say you start off with a gas at a very high temperature and the gas cools down. Its temperature decreases from this point to this point. until the gas turns into liquid, the temperature does not change. Always remember, during state change, the temperature never changes. And when the gas has turned into liquid, and when you're cooling it, the temperature decreases. But the moment it reaches the freezing temperature, until all of the liquid turns into ice or solid, the temperature remains constant. And the same concept applies whenever a matter is changing its state, the temperature does not change. And then you have heating curve. Same, you start off with a solid, reaches the melting point until all of the solid melts into liquid, the temperature remains constant. When it becomes liquid, you heat it up, the temperature increases. When it reaches the boiling point until all of the liquid turns into gas, again the temperature remains constant. And once the state has changed, now if you apply the heat, the temperature would increase. One last time, when matter changes its state, the temperature doesn't change. Next. And this is a very common experiment to determine the specific heat capacity of a material. So the whole underlying principle of this is there is an electrical heater. Okay, so the energy you supply to the electrical heater is in the form of electrical energy, of course. So the whole idea of this experiment is electrical energy is transferred to thermal energy. Okay, now you break this down. What is the equation of electrical energy? It's V by T equals to, and the equation of thermal energy is mc del, actually for IGCSE, it's del T. So the whole idea is to determine the specific heat capacity, C. So for that, you need to measure the voltmeter reading, ammeter reading, and how long you are switching on the heater using a stopwatch. Measure the mass using an electronic balance, measure the initial temperature and the final temperature, and calculate the change in temperature. And just make C the subject of the equation. And since it's an experiment, a common point for all experiments in general is repeat the whole experiment. No, for this specific experiment, it is repeat the whole experiment and calculate an average value of C. Next, in magnetism, as in Unit 6, there is a very important concept where you need to figure out the direction of deflection of a moving charged particle. Always remember that current is in the same direction as motion of a positively charged particle, and current is in the opposite direction to the movement of a negatively charged particle. And also remember that a dot represents magnetic field out of the page and a cross represents magnetic field into the page. And the direction of deflection is found out using Fleming's left-hand rule. Then they can ask you about construction of a transformer. So the coil with which there is a power supply is called the primary coil, and the one that doesn't have a power supply is the secondary coil. So the way transformers work is alternating current in the primary coil produces a changing magnetic field. The core, this is the iron core, becomes magnetized, and the field changes to the secondary coil, which induces a voltage across the secondary coil. And calculations are also very common. Using turns ratio, it's voltage in primary by voltage in secondary equals to number of turns in primary by number of turns in secondary. And every time in a transformer question, they give you any reference of, let's say, current, then you have to assume that this is an ideal transformer, as in power output is equal to power input. Now you break down power. Power equals to VI, and for output, this is the secondary, right? You get the output from the secondary. So voltage in secondary into current in secondary, and input is coming from the primary, as in voltage in primary times current in primary. So one last time, every time in a transformer question you come across current, you have to recall this equation and assume that it is an ideal transformer, meaning power output equals to power input. Then you also need to recall uh, how step up and step down transformers are used in the transmission of electricity. Okay, so why do you step up before transmission and why do you step down before transmission? And they can also ask you about the magnetic field around um, an electromagnet. Okay, and how do you know that field is flowing in this direction? So this is where you need to apply the right hand grip rule. So see, current is flowing in this direction. So on the front face, this is on the front face, right? This is the direction of current. So on the front face, this is the direction of the current. And when you grip with your hand, with your right hand, of course, the four fingers align with the direction of the current and the thumb. So if you apply right hand grip rule here, so the four fingers are aligned with the direction of the current. So you see the thumb is pointing to the left, meaning this end is my north pole, meaning this end is my south pole. And we all know field lines always flow from north to south. So this is very similar to the field lines around a bar magnet. The only avenue it's different is you don't show the field lines through the bar magnet, but when it comes to electromagnets, you do show the field lines through the electromagnet. And you also need to know the field shape of the field and direction of the field around a straight current carrying conductor. And this is concentric circles. And again, the direction is found out a bit differently this time, again using right hand grip rule. So for this scenario, the thumb indicates direction of current and the direction of the grip indicates direction of magnetic field. So if we apply right hand grip rule here, this would be the shape and direction of the magnetic field around a straight current carrying conductor. Then in astrophysics, you have these two terms, apparent magnitude and absolute magnitude. So let's say you have two stars and you just view them from Earth, okay, where they are. So it appears as though the star has this brightness and it appears as though the star is this amount, this has this amount of brightness. But this is not a proper comparison. The proper comparison would be to consider them at a fixed distance or at a standard distance. And this diagram represents absolute magnitude. And this is actually the definition of absolute magnitude. It is the measure of the brightness of a star at a standard distance. Then this is actually common in paper 1 as well, but I have been noticing they give half-life calculations in paper 2, right? So a sample of uranium has an initial mass of 60. Calculate the mass remaining 46 after 46 minutes. So this type of questions you can always answer with graphs or with a table as well. So the y-axis would be mass because the question is asking you about mass, and the x-axis would be time. And we all know as radioactive substances decay or isotopes decay, their mass also decreases. The question would have been about activity as well. Okay. So the initial mass is 60 and half-life is 23, right? So in 23 minutes, 60 drops down to 30. And this is literally the definition of half-life. So half-life is the average time taken for half of the radioactive isotopes to decay, or the activity to half, or the mass in this context to half. So this is 23 minutes. And in another 23, as in after 46 minutes, this will half again. So half of 30 is 15. So after 46 minutes, the mass remaining would be 15 gram. You could have answered this using a table as well. Okay, now coming back to astrophysics, this is very, very, very common. The two pieces of evidence for Big Bang. So one is CMBR, the other one is redshift. So you need to know the detailed description of these two phenomena. Also, you need to know the HR diagram, where the y-axis represents absolute magnitude and the x-axis represents time, but the time increases to the left. Okay, generally we increase the quantity to the right, but the only exception is with HR diagram where the temperature increases to the left. Okay, this is the temperature axis. This section is called the main sequence. This is giants, red giants, and these are red supergiants, and this is white dwarfs. You can leave out this part altogether if a question asks you to identify. So the three main components are main sequence, red giants, and white dwarfs. Okay, this is really important. Doppler effect calculations. So the stationary source on Earth is our reference value. Okay. So when you compare spectral lines, you'll see that lines are shifted towards the red end of the spectrum when it comes to distant galaxies. And with these pieces of information, you can actually calculate the speed with which these galaxies are moving away from us, right? So for these questions, Doppler effect calculations, we always recall the equation del lambda by lambda equals to V by C. And I hear a lot of times students confused. Del lambda is so obvious because a line corresponding to the green region from the source on Earth has a wavelength of 530 nanometer. Okay, this is the source on Earth. The same line on the spectrum from light from a distant galaxy has a wavelength of 532. So del lambda is so obvious. It is 532 minus 530, that is 2 nanometer. Now question arises, what should be lambda? Which one do I consider to be my lambda? Do I consider 532 or 530? Answer is also very simple. Always remember, the denominator is always the source on Earth, that is 530. This is 530 nanometer equals to V by C is always the speed of light. And the value for the speed of light is 3 times 10 to the power 8. Nanometer gets cancelled out. So the value of V that you get is 2 times 3 times 10 to the power 8 divided by 530, which is 1.1 times 10 to the power 6. Generally, this velocity is in the power of 10 to the power 6 meter per second. And this velocity is what you call the recessional velocity. And recessional means the velocity with which the galaxies are receding. So recessional comes from recede, that is moving away. Speaking of moving away, so here you have some more spectral lines, okay? And in this here, the question asked, which galaxy is the farthest away? All right, so pick this line because this is easiest to identify. Always remember the electromagnetic spectrum, as in the visible part of the electromagnetic spectrum. This is the blue region, this is the red region. Blue or violet, right? So you can see that the light from galaxy C is the farthest away compared to the laboratory source, as in from here, this one is shifted the farthest, okay? So this has the greatest redshift. Greater the redshift, greater the velocity, and this means that this galaxy is the farthest away. And finally, you need to know when do we use a bar chart and when do we use a line graph. Bar charts are used when the data is discrete or categoric or discontinuous. But line graph is used when the data is not discontinuous, as in continuous data. Okay, for example, time, speed, these are all continuous data. Okay. Speaking of data and variables, in any experiment, there are three types of variables. Go through the experiment sheet. This will clear up your confusions. And good luck with your exam tomorrow. Let me know how it goes. And do write in the comment section where you are watching my video from. And if you are already not subscribed, please subscribe to my channel. And good luck with your exam once again. Take care.